Alright, so what I want to do right now is just give you a couple of examples of how to determine the centripetal force. Like I said, this is one of the trickier things to do, and it does take practice, and that's what I want to kind of give you right now. So what I would ask you to do is just to take a moment and pause after I explain each of the scenarios and try and figure out what the centripetal force is, what the equation for the centripetal force would be at different positions on, say, this first one here. Assume that this can go in a perfect circle, so you have these 4 positions to look at. So this is a conical pendulum. It's like if I were to take this and move it in a horizontal circle, but my string was at an angle, and let's assume that it's in the air, so something kind of like this. So the string is at an angle as it moves around the circle. You would assume that this was at a constant angle theta, that it maintained that angle, and you'd have like the length of the string. This would have like some known radius type idea. This is like a car going over a hump where it's just like the car is sitting on the hump, like a speed bump type idea, or like a big hill on a roller coaster. Just assume that it's sitting on the track and it's not being held in place somehow. And this is one of those cool, I don't know if you've ever been at this at like an amusement park or a fair, where basically it's a circular cage. Sometimes like it's like a spaceship sometimes. And basically what they do is they line the people up all around the outside. You're standing there and it spins you really, really fast, kind of throwing you up against the side. The really cool ones, like the high-end ones at like amusement parks like Six Flags, they'll even drop the floor so you're suspended in air up against the wall. So we're going to assume, like on this case, that the floor has been dropped, and so basically they're being shoved up against the side, moving in this circle, you know, at some radius from the center. So what I want you to do is pause and try and figure out in each of the positions shown, so the 4 positions here, the 1 here, 1 here, 1 here, what the equation for the centripetal force is. Please try it yourself first. Kind of like I did on the circular motion video. So pause for that. And then when you think you have answers to all of that, come back. All right, so let's start over here at this one. We have 4 different positions. So we're assuming that basically it's just in contact with the track. And so it's basically just kind of sitting there. It's not being held in place. So if I take a look what's going on here, then basically I have gravity pulling me down. And basically what happens is I'm trying to move in a straight line on the cart, but the cart, if it moves in a straight line, collides with the side. And what that does is that actually creates a normal force, and normal force is always perpendicular to the surface, so my normal force points towards the center. So in this case right here, my centripetal force is just going to be my normal force. In this case here, my gravity is going to be pulling me down. And as long as I'm going fast enough to make it around the circle, I'm going to have my normal force still pulling it. If I'm going really fast, I'm going to have a really big normal force. So I'm going to have both a gravitational force and a normal force there. So in this case, I'm going to have normal force plus my gravitational force being my centripetal force, which was kind of like that vertical circle with the tension. Now, a special thing about this, it is possible to go all the way around the circle without falling off. And there's some minimum speed required to do that. So this is kind of a really good point with this one. So if I take that equation, my centripetal force is normal force plus gravity, then my centripetal force is equal to m times my centripetal acceleration. Then I have normal force and gravity is mg. My centripetal acceleration is tangential speed squared over r, which is normal force plus gravity. So if I were to look for this, I can actually find basically the speed that I need to go at to go around the circle. Well, the faster and faster I go, my mass is constant, my radius is constant. So if I'm going faster and faster and faster, mass is constant, g is constant, my normal force is going to change. So I can actually solve for normal force here. My normal force would be m bt squared over r minus g. And I just kind of moved that over, subtracted that over here. So basically what this tells me, M and R and G are all constant. So the faster I'm going, the bigger the normal force is. Now, the slower you go, sometimes when you're on a roller coaster like this, if you're like on a one that doesn't go super fast, when you get to the top, it's actually scarier almost than when you're moving super fast. Because what happens is, remember that normal force is responsible for our feeling of weight. And if you've ever been on a loop, upside down loop like that, sometimes it feels like your stomach has dropped out. And you feel weightless. Well, your feeling of weightlessness or almost weightlessness comes from having very little normal force. So what this is telling me is the faster and faster I go, the bigger and bigger my normal force is. Well, if I wanted to find the minimum speed to go around the circle, and not fall off the track, and we call that losing contact, what would I have to assume? Well, I can basically have contact with the table here and not put any pressure on it. If I don't put any pressure on the table, then I don't have any normal force. So if I'm just kind of hovering, so I'm kind of in contact but not actually exerting any force on the table with that contact, then I have no normal force. So basically, the minimum speed I have to safely go around this curve and not lose contact would be with my normal force equaling 0. And that would be the speed just to make it. If I go any faster, my normal force would get bigger and bigger and bigger. So what that means is we could come up to this equation, and if I wanted to find that minimum speed to go around the circle, basically what I would assume is I would assume that my normal force is 0, and then MAC is equal to mg. So my centripetal acceleration is equal to g. So when I'm at the minimum speed to go around the circle, when I'm at the top, this is the minimum speed at the top, then my centripetal acceleration is just equal to g. And if I would want to find the speed, I would sub in vt squared over r is equal to g. And that would give me that my tangential speed would be rg square rooted. And this would be the minimum speed to go around the loop. And any faster I go, I'm going to have normal force. That normal force will get larger and larger and larger. But if I go any slower than this speed, then basically I'm going to fall off and it wouldn't be safe. So if you look at these variables, basically my radius is important. So the bigger the radius of my circle, the faster I have to go to make it around. So I have to be going really, really fast to make it around a very large circle. If my circle is smaller, I don't have to be moving as fast. So I could find that minimum speed to make it around the circle. So kind of cool thing with that. And they often ask you for that minimum speed to make it around the circle. So continuing along our path, when you're on this side here, you're going to have gravity down and normal force towards the center. So once again, your centripetal force is going to be normal force. And we're at the bottom, assuming we're still maintaining a perfect circle. So this is like if I was going into the curve. My gravitational force would be pointing down. My normal force would be pointing up. So remember, my centripetal force is the difference between those. It would be normal force minus gravity, because gravity points outward. Normal force is inward. So if I want to go around the circle, my normal force has to be bigger than gravity to actually make it, to start going around that loop. If my normal force is not large enough, then I won't be able to go around the loop at that point. So, and then the faster and faster I'm going, once again, the bigger the normal force is. And I can tell that because if I sub in over here for MAC is equal to normal force minus FG, and VT squared over R is equal to FN minus FG. If I solve for Fn, I get that Fn is equal to Fg plus mvt squared over R. So since my gravitational force is constant, the bigger and bigger my speed gets, the bigger and bigger my normal force gets. So you can learn a lot about the centripetal force and the normal force, and the normal force is very variable throughout this, about what's going on with your speed. All right, so those are our equations for that example. Looking over here, this one's kind of tricky. I have a gravitational force pointing down. I have a tension force pointing at an angle. So when I'm looking at my circle, the radius of my circle is here. So neither my gravity force nor my tension force point directly radial, but part of my tension force points radially. So I have, and part of it points tangentially. So this would be like FTY, and that would be FTX. And depending on the angle they give you, you have to kind of be careful. So this angle right here is not the same as that angle. That angle would be 90 minus theta, as you realize there. So a lot of times it's actually easier, instead of resolving this triangle, is actually coming over here and resolving this triangle. So FTX and FTY, because if that's the angle that they give you, that's the same as this angle right here. If I wanted to write my equations for this based on theta, my centripetal force would be FTX. In the y direction, just so you know, in the FY direction, if this thing is maintaining a constant horizontal circle, your FTY minus your gravity would have to be 0. That wasn't part of the expectations, but it's just something important to know, because this will help you solve problems. Because if you know what your mass is and you know what your angle is, you can find your FTY. And FTX, based on this triangle, would be the opposite side, so that would be FT sine of my angle theta. So my centripetal force here would be FT sine of theta. And then once again, you could find different things. You could find the speed. The tricky thing here is you're not given R, so you just have to make sure that you use trig to relate the length of the string in your angle theta to find your radius R. So you have to be careful with that example. All right, looking at this example here, going up over the circle, I'm going to have gravity pulling down, and I'm going to have normal force pointing up, because I'm just sitting on the circle at that point. But remember, I am moving with the speed. So even though it looks like it's just sitting there, because I have a tangential speed, a speed tangent to that circle as it moves over it, that means that I have a centripetal force. If you have a tangential speed, you have a centripetal force. So my centripetal force is going to be, in this case, my center pointing force is Fg, and Fn is opposing that. So it's going to be Fg minus Fn. They are not equal to each other. And that's one of the big mistakes that I often see, is people set the vertical forces equal to each other, and that would mean there was no centripetal force. Another thing that they do is they ask for what is the minimum, or actually in this case it would be the maximum. What is the maximum speed? You can go to not lose contact. So it's kind of the opposite of this one over here. Because if I go too fast, if you've gone this over a speed bump, you go airborne, right? You're not in contact anymore. So if I take a look at that centripetal force equation, it's going to be Fg minus Fn, then if I look for that speed, I'm going to once again do the MAC is equal to mg minus Fn. So if I don't want to lose contact, at the point right before lose contact, once again, I'm touching but not pressing. So we're going to also assume that our normal force goes to 0 at the max speed to not lose contact. So once again, mass cancels out of this. So it's really cool in both of these situations, the mass of the car doesn't matter. There's still, in this case, a minimum speed that it takes to go around. In this case, a maximum speed, and it's independent of the mass of the car. Your AC would equal G, and your VT squared over R would equal, oops, didn't write that, would equal G. So once again, your VT would equal the square root of R over G. And what this tells you is the bigger the radius, so the bigger the radius of this hump, the faster you can go without losing contact. And you've probably seen that going around speed bumps, because you're probably a teenager that doesn't necessarily always slow down for speed bumps. And if it's a really low flat speed bump, you can go pretty quickly over without losing contact. But if it's one of those like pointy speed bumps, and you go flying, you're going to go flying, and you're going to get a bunch of shaking, and you're going to hurt the suspension of your car. So don't do it. Obey the speed bumps. They're for your safety and everybody else's safety. Okay, so you got that same, but this is actually a maximum speed, where it's the same equation over here, but it was a minimum speed. And remember, don't just memorize equations like that. You'd have to prove it in an AP problem, but it gives you kind of a little hint. Now, this problem right here is one of my favorites when we are looking at some of the different aspects of centripetal motion, because this is not one that we experience kind of every day, so it's harder to think about. So what forces are acting? Well, gravity is obviously pulling me down. I'm being pressed up against the wall. The wall is here, so I do have a normal force, but my normal force is perpendicular to the wall. So what's keeping me from sliding down the wall? Well, that's friction. So my friction force actually points up, and it is a static friction force. So if I were to look at the y direction, in the y direction, my static friction force minus my gravity would be 0 if I'm staying in place. And then over here, my radius is here, so it's actually the x direction is my normal force, and that is what's equal to my centripetal force. So your centripetal force is normal force. It's not friction. So there's a certain speed where you wouldn't even need, basically there's kind of like this minimum coefficient of friction needed for you to not slide down the wall, but to go around in circles, once you're already moving, you'd be going. Now you need some friction to get moving, because it's friction that would actually allow you to move with the sphere. But once you're moving, you don't technically need it, except for not to fall down. So with this type of problem, our centripetal force is our normal force, but remember that our friction force can also be related. So if we were looking for the maximum static friction before you start to slip, then your Fs max would be mu times normal force. And so sometimes when they're looking, they might give you a coefficient of friction, or might ask you to find the coefficient of friction. And you can do that with circular motion, because your normal force is going to be related to your centripetal force, which will be, once again, be MAC, which would be mv squared over r. And you can go from there. By the way, I don't think I mentioned it before, but on the AP formula sheet, they don't use the T for tangential, they just use a V. But it means the same thing, because that is your only speed in that case. So I hope that gives you some examples for how you can analyze the centripetal force, and also how you might start solving problems. All right, have a good day.